I bring you back now to the stratospheric injections. My talk I will split with Markus, who will be then talking more about experimental chemistry, and I will cover all the modeling side. So one of the results of our first year is that we agreed on the short name of the project, which is Solpargio now. And then, as you can see, our project is about both chemical and climatic impacts of solid particles. And I first remind you what do we have in terms of the structure. So we have two work packages for experimental chemistry. And we have two because they use different instrumentation, but actually it's one PhD student doing that. Celia, she's here. So if you're interested about technical details, you can chat with her. Then we have a work package focusing on modeling of chemistry, stratosphere-troposphere coupling and stratospheric dynamics, and tropospheric impacts. And actually for the last two work packages, we only recently hired staff. And for the work package 5 and the Indian Institute of Tropical Meteorology, they started months ago, and in Madrid, the Spatial National Research Council, the student will start only in autumn. Therefore, some of the results they are delayed, but nevertheless, we already have results everywhere. And we also already started collaborating with these 4 other projects by sharing results, data, discussions, experiment plans, and so on. So, it has been already covered today. 2 main concerns about sulfate, sulfur-based SAI is that it hits the lower stratosphere and that it can also alter the ozone layer. And actually, a lot of impacts on the ozone, they come not only from the heterogeneous chemistry, but also from the dynamical impacts. And ideally, what we want from the SAI particle, that it would have these properties, so no impacts on the ozone layer, no absorption in the long wave, so there's no heating in the stratosphere, high backscattering efficiency, small mass, so it can live longer in the stratosphere, and no health and biosphere impacts. From the clouds, I don't know what we want, because in principle, if they sediment back to the troposphere and then suppress a little bit the long wave effect of the cirrus clouds, that would be a win-win situation. But this still needs to be explored. And to highlight the importance of the dynamical effects here, there's a figure from our recent paper. So where on the left side we have side effects because of the sulfate SAI in surface pressure. So it's the difference between the climate we want to have and the climate we can have with geoengineering. So all the anomalies are side effects. And on the right side, it's the same, but in this case, we switched off the aerosol absorptivity. And as you can see, many of the effects are now gone. And actually what we have now in the southern hemisphere, that's the effect of the intensified ozone hole. And so question is like, can we still somehow use sulfur? Because there have been a lot of research on that when people try to manipulate the emission scenarios, where to put sulfur and how much and when in the stratosphere. And here on the left, you see then there's different emission scenarios: equatorial, 15 to 15 degrees north and south, 30, 30, and 60, 60. That's from the UK ESM model. And on the right side, that's from the vacuum model. And indeed, by emitting sulfur not exactly at the equator, you can then reduce the local heating in the stratosphere. And then also you have more homogeneous heating in the stratosphere. And that's what matters for the dynamics, because then you need to care about meridional temperature gradient. By reducing the meridional temperature gradient, you'd also then reduce the impacts on the stratospheric dynamics and the surface circulation. Also, it has importance for the ozone. So that's from the same Bednar's paper. And you can see here that for the polar and 30 and 30 to 30 degrees north and south cases, So the ozone anomaly flattens everywhere except the southern polar region where the heterogeneous chemistry dominates. So, but still, we can say that, okay, we can now reduce the dynamical impacts of sulfur by manipulating the emission scenarios, but still there's a chemical impact, and as well it still absorbs, so it still traps the long wave, therefore there's still impacts on the diffuse radiation in the atmosphere. And then to highlight a little bit further the ozone effects, here again we have the ozone side effects with the absorptive sulfate, and that's a pretty canonical pattern of how ozone would respond to sulfur-based SAI. And a lot of these anomalies are because of the dynamics. So basically what you do, you slow down the shallow branch of the Breuer-Dobson circulation, so you slow down this transport, but you accelerate the deep branch of the Breuer-Dobson circulation, so you accelerate the transport of ozone like this. Plus, it's not only about the transport of ozone itself, but also of other traces in the atmosphere. In addition, you will intensify the polar vortices, and therefore you will kind of decrease the mixing through the polar vortex barrier, and also intensify the ozone hole dynamically, because now it will be colder conditions. So dynamics affects a lot of this, and to show this, here's the result when absorptivity has been switched off for sulfate, and now we have a nice 2 layers of heterogeneous effect when we have in the lower stratosphere chlorine activation on the aerosol surfaces, and a bit higher up nitrogen deactivation through hydrolysis of N2O5. So therefore, yeah, dynamics is also important, and the heating, stratospheric heating, therefore, is important for the ozone. And yeah, so we wanted to look at all these alternative materials to see if they're like better ones compared to sulfur, and we used our SOCOL model, and this has been programmed by Sandro, who introduced the microphysical part, and basically then we calculate how these particles interact with each other, how can they interact with the background sulfate, and then they can grow by building these agglomerates, and then if they grow large, they can sediment down to the lower levels and to the troposphere eventually. They are advected by winds, and in the troposphere they are removed through wet and dry deposition. And we tried different materials, as you can see here, and this is basically the cooling efficiency. So it's burden and injection rate per watt per square meter forcing. And yeah, so here you also see another advantage of SO2, that in case of SO2, you don't need to bring the whole mass into the stratosphere. Half of the mass is already there, so therefore, in terms of injection rate, its efficiency increases. And so we then also looked at the lower stratospheric heating of all of these materials, and indeed there are ones that have less absorptivity in the long wave, so there's less heating, and based on these results, we then decided to focus on alumina, calcite, and diamond as the most promising ones based on their reflective and non-absorbing properties. Yeah, and why at all this complexity in the model, all this microphysical treatment is important? Why not just prescribing the optical properties, the extinction, and then run the model? It's because the microphysical interactions are important. That has been shown already today by Simone and others. And here's an example. So here you can see the level of agglomeration. So like different colors correspond to different fractals, and how it depends on the size of the initial monomer. And here you can also see how then for the same size, it would depend on the emitted mass. So there's a lot of the dependence, and if you just prescribe the optical properties, you will lose this complexity. And another result is here. So it's a normalized backscatter cross-section for diamond agglomerates. And here's normalized by the spectral solar irradiance and the stratospheric lifetime of the particle. Therefore, in this case, is the effect of both increasing size and decreased backscatter efficiency, but also the reduced lifetime, so that they simply fall quickly back, and therefore the 16 MERS are not effective almost at all in helping climate. So therefore, all this microphysical complexity is important for the resulting effects, as you can see. And since all our lab work only started in the first year, and like all the microphysical lab work also, we decided first to focus on what we have. And we performed the experiments with chemically inert materials. And we performed this G6 future runs that Romaric already introduced today. And here you see end of the century side effects for the surface pressure for different materials. And again, you see that non-absorptive particles like calcite and diamond, they almost don't have surface pressure side effects compared to sulfur. And the same for surface temperature. You see that there are much less of these side effects. And then we were also looking regionally at different processes that result from this. For example, the North Atlantic Oscillation. That's basically the index defining the circulation here in the North Atlantic. And it shows the position of the jet stream and how wavy it is. And here we see the SSP2. So that's what we want to have. So that's the target climate. SSP5, so that's the climate change effect. And 4 geoengineering cases. And what we see that the non-absorbing ones, they are the closest to the target climate, and the sulfur case can be even worse, so that the climate change itself for this parameter. And then same for the southern hemisphere, so it's also a dynamical index showing the position of the jet and its waviness. And again, you see that diamond and calcite are the closest to the target climate. Then we also looked at the Arctic region and the sea ice thickness, so that's 4 seasons, sulfur case, diamond case, and the climate change itself. And you see that in case of sulfur, there will be much more thinning of the ice compared to diamond. Another thing we looked at is the Atlantic meridional overturning circulation, which is one of the main climate tipping points. And here you see the climate change effects. So there's a slowdown of AMOC and the slowdown of the Gulf Stream. And what we found that all 4 materials, they can slow down the slowdown or stop the slowdown. And there we didn't find a strong difference between or like compared to sulfur. Another parameter we looked at is tropical tropopause height. And here the difference is very pronounced. Because then, well, you don't have this heating in the lower stratosphere, you don't push the tropopause down. And therefore, the tropopause is higher in non-absorbing cases, and then it's also then the closest to the target conditions. And this will then impact the deep tropical convection, the tropical cyclones, as you showed today, because basically impacts the stability in the tropical region. And another one is Arctic amplification. So that's delta T in the Arctic divided by delta T global. And in this case, it will be like mitigation by reducing CO2. And this is mitigation by doing our geoengineering. And again, sulfur is the worst. And then non-absorbing ones are the best and the closest to what we want to have. And another thing we looked at was the hydrological cycle side effects. And here you see the precipitation decrease or drying, global drying, in the case of calcite, diamond, alumina, and sulfate. And what we see that in the absorbing cases, there's more drying. And to explain it, we need to look at the radiation balance. So in case of sulfate, we need to reduce the short wave more because there's more long wave trapped in the system. So there's less long wave emitted back to space. Because of that, the surface, we also get less short wave. But this is for the same long wave because this is the same surface temperature. And this needs to be balanced by something. And this is balanced by the reduction in latent heat release, so evaporation, which then drives the reduction in precipitation. So basically, you reduce more the short wave, and short wave is more efficient in affecting the evaporation than the long wave. And for the same global mean surface temperature, you therefore then have a drier climate. And yeah, we now also explore all the regional. There are a lot of regional details in this, so it's like a global radiation balance view and the feedbacks. So this is a work in progress. Yeah, and we also try to model the chemical side effects of the solid particles. And it's different between alumina and calcite. In case of alumina, it depends on the size of the particles. The particle is large, then sulfate will create these islands on its surface. And where it's sulfate, it will be a sulfate surface chemistry. Where it's pure alumina, there is also alumina surface chemistry, which is very uncertain. And if the particle is small, it will get fully coated by sulfate. And for the calcite, it's different because it's a base, so it reacts with the stratospheric acids and creates these salts. And then the question is how they are formed, what are their diffusion inside the particle, what are the uptake coefficients. And this is super uncertain. We tried to gather all the info that was available from the literature. That's what we got. So here you see effects on the total ozone column, exploring these uncertainty ranges from the literature. And what we found that for all these additional new alternative materials, it's much more uncertain than for sulfate. It can be worse than sulfate, worse, but also better. And yeah, to reduce the uncertainty, we need new lab data. And that's what we do in work package 1 and 2. And now Markus will talk about that.
Okay. The microphone is on. Good. Yeah, thank you. Okay, so hello from my side as well. So very quickly, I will bring you a little bit back to the world, to the reality of lab experiments, right? And from global scale to nanometers, actually. So as mentioned previously, also this morning already, so what we need to do is really to try to understand a bit the molecular level details of uptake of these gases. So we have focused in the first year entirely on the chemistry with calcite particles and looked at the uptake of HNO3 and HCl. And we have to be aware the HNO3 concentrations are pretty low in the stratosphere. Also temperatures are low, water vapor pressure is low. The problem is a little bit, and this is what Timofei just said, the uncertainty is extremely high in terms of the kinetics, so the uptake coefficients, which is the rate, the normalized rate at which a gas is taken up by the particle. So essentially the probability that a gas kinetic collision leads to its loss to the particle phase. They range based on lab experiments over many orders of magnitude, and the details in how they depend on time or gas phase concentrations are very complex. So we need to measure these, and since also we deal with mostly long time scales, we also need approaches that can at least to some degree tackle those time scales. And so we used in the project two methods. And one is X-ray photoelectron spectroscopy at ambient pressure, so that's why it is called ambient pressure. And then the other one is heavy ion elastic recoil detection analysis. So in this method, you are shooting heavy ions into a sample. These ions scatter on target atoms of the sample. These target atoms, the recoiling atoms, are getting energy in that process, are moved out of the sample to a detector, and then by measuring the velocity and the energy of these recoiling atoms, you can determine the mass and the location where they came from. Yes, it's good. So then you get such elemental depth profiles after exposing a sample. So this is offline, not in situ. The other method, X-ray photoelectron spectroscopy, you irradiate it with X-rays. These X-rays are ejecting electrons from the sample through the photoelectric effects. These electrons are going to a detector. We measure the kinetic energy distributions, and from that we can determine which elements are there and also in which chemical environment they are. Photoelectrons scatter strongly in the sample, and you can only see photoelectrons without inelastic scattering from the top few nanometers. And so we can determine, with XPS, we determine the surface composition. With HI-ERDA, we can look a bit further deep into the sample. And so, of course, you need some machinery. So this is the XPS end station at the Swiss Light Sort. So this is a synchrotron-based method, and this is the heavy ion beam facility in the laboratory of ion beam physics at ETH Zurich. So I'm not so familiar with this method, and the colleagues, and none of that group is here, but maybe Sandro and Celia, who has started recently about it, can also maybe provide some more details. No, I pressed the wrong button. So just one example from ERDA. So here you see a depth scale in nanometers, and you see how nitrogen has penetrated into a calcite single crystal over 10 days when exposed to 0.8 ppm HNO3. And from this profile, we can then try to back out an effective diffusion coefficient of this process, so which is in the order of 10 to the minus 17 square centimeters per second, which is kind of reasonable for a diffusion limited or driven process in a solid material. XPS experiments here. So we have heard a lot about Sandro's work in the modeling domain, but actually Sandro also spent some time in the lab at PSI at our XPS end station. So the way we do this, we deposit a powder on this substrate here, and this is cooled from the backside to stratospheric temperatures, so 210 Kelvin, for instance. Then we move this sample in here, and then we expose it to a mixture of water vapor and some carrier gases and HCl or HNO3. And then we can, so this is why it is called ambient pressure. So we really have stratospheric conditions in terms of temperature, water vapor, and trace gas partial pressures. And then we measure in situ, we measure the evolution of the surface composition. So here you see, for instance, the pink line is, so this is the carbonate peak before we start dosing HNO3. And then when we dose HNO3, this carbonate peak here from calcium carbonate is going down, while at the same time the nitrate peak, which is not here before exposure, increases as a function of time. And then we do some magic analysis and a lot of evaluation, and from that we can determine the thickness of this layer. So what you see here is for different experiments how the thickness in nanometer of the calcium nitrate layer evolves as a function of time over times of roughly a day, because these beam times are very expensive and very competitive, so we cannot spend 6 months there to watch one sample. And the same we can do for calcium chloride after exposure to HCl. So we always see this increasing layer thickness for different experiments under different conditions. So here we can really constrain the uptake coefficients and plot them together with the other data. So these are this large scatter of data available from the literature that were obtained under different experimental conditions. So we have now placed our measurements here. So these are the updated XPS uptake coefficient derived from these layer thicknesses as a function of concentration and time. And here are the ones from the HI-ERDA. So they more or less seem to lie on such a line, so that there seems to be some time dependence. And the same for HCl. We also have, yeah, he will wrap up. Oh, okay, so we are already done. Good. Just one, because there has been, and I think this was discussed here also already in the past, I heard last year. We also did some offline experiments where we looked at what happens when first the particle is coated by sulfate. So in these experiments, we first exposed at room temperature a calcium carbonate sample to sulfuric acid solution. And then we see the sulfur peak here evolving after this. There is also a little bit of nitrogen from the exposure of the sample to air before actually doing the experiment. When Celia did these experiments, when then she did the same experiments directly exposing a mixture of sulfuric acid and HNO3, and of course the HNO3 vapor pressure of this solution largely dominates, then she only see a nitrate peak. So obviously sulfate was not coming up then at this moment. When you do first form a sulfate layer and then afterwards expose it to HNO3, much less nitrate is formed. So the sulfate seems to protect the surface from reacting with HNO3. And I think with this, I just hand back to Timofei. So we hope to continue these experiments and getting more quantitative on this, and also to provide better informed parameterizations for the uptake coefficient so that we can then finally reduce these large uncertainties on these.
Right. So this we skip. And I go to the summary. It's useful summary for the day because it's here I grouped it as the source of uncertainty in impacts of solids on the system. And so on the chemical properties, so we have what we have done so far, we used all the available data, put it in the model, and we found that the results is very uncertain. That's why the lab data is needed, and that's what we are doing now. And on the right column, I put the projects that in bold, the ones we already collaborate with, and the other ones that we will be happy to collaborate doing the same. And then for the near field microphysics, again, we used the best we could, and we showed that this microphysical complexity is then very important for the resulting effects. And again, all the lab work that will result from adjacent projects will be welcome for the final experiments with our model. Same for the optical properties. The ones we use so far show that all these alternative materials that we tested, they're better than sulfur in the long wave. In the short wave, diamond is also better. For the aerosol-crowd interactions, there were some activities shown today, and hopefully by the end of the program, there will be something you can also put in the model. For the global and regional effects, what we found that all of the alternative materials that were considered, they were mostly better than sulfur so far. But we need now to do new emission scenarios that will not just replicate the ones for sulfur, but will focus on what would be the best for these solid particles. And this has not been done yet at all. And for the multimodal estimates, as Simona said, we designed the first solid particle MIP, where there will be several models. And plus, we also participate in and lead adjacent MIPs for sulfur. But it's still important because we always compare everything to sulfur. Therefore, by learning more about multimodal uncertainty there, will improve our understanding of the solid particle impacts. And for the health economy and the biosphere, we will look at the effects on the photovoltaic systems. That's all we could do in this part. Sorry that it took longer. That's it.